Hey everybody, welcome back to another round of physics, and yeah, let's get going. We are now at a stage where we are going to progress from the electric field to another physical quantity. And this other physical quantity, which we call the electric potential, is related to the electric field in the same way that we relate forces and potential energy. So the first thing I thought I might do is refresh our memory regarding forces and potential energy. First of all, we go back to the definition of work. And work is defined as a force dotted into a displacement. Now you notice I've used derivative notation here, but in past iterations we might have said something like the sum of a force times a displacement. And if the force happened to vary, then we would have to chop our displacement into tiny sections over which the force is roughly constant. And then we simply summed up the total. Now, there is a very special case where when we start at a given location and we end at a different location, there are a group of forces where it does not matter how we get to an initial spot and a final spot. The only thing that matters is the starting and end points. And when we have those types of works, we call the forces conservative. Under that circumstance, when we are dealing with a conservative force, we can write a direct relationship between the potential energy and the work done. Now remember, again, just as a reminder, the potential energy is talking about energy that is within the system, whereas work is dealing with the interaction between the system and the surrounding. The distinction between these two, say, for example, if I'm dealing with gravity, perhaps here I would put, I don't know, Greg and the Earth as the system. And then we would talk about the gravitational potential energy between Greg and the Earth. Conversely, if we decide to talk about work, then we would talk about the system as being Greg and the surroundings being the Earth. And then we talk about the energy that the Earth puts into the system, or perhaps the energy that is removed from the system. Okay. Now we can only do that when we have a conservative force. Now because of that, if we take those two ideas and smash them together, we see that we can derive an expression, okay? Namely that a change in potential energy, which is equal to the work, is equal to F dotted into dr. Or we could rearrange it to come up with the force is equal to the negative potential, is equal to the slope of the potential energy times a negative sign. And that in particular is what allows us to go into energies, a scalar quantity, rather than talking about forces, a vector quantity. Perhaps you would prefer a graphical interpretation, which is perfectly fine. Let's say that I plot the potential energy as a function of distance. Okay. And if you want, you could literally think about this as the gravitational potential energy. And you know, gravitational potential energy is simply mg times, for lack of a better term, I'll say your height above the ground. So you could say that this plot is just simply the height above the ground. And you'll notice if I'm at one particular location, let's say I put a ball right here, and we notice, first of all, if the ball is rolling down that slope, first of all, we say, well, how is the potential energy changing? Is the final state greater than the initial state or vice versa? And you say, okay, the final is less than the initial, so the change in potential energy is less than zero. Furthermore, How about our distance? As we moved, our final distance is larger than our initial distance, Ri. And so we know that our delta P is less than 0, our R is greater than 0, and so because we have a quantity less than 0, the negative sign from the change in potential energy cancels the negative sign out front, and we get that the force is in the same direction as the displacement. Well, how about if we choose some other spot where our initial is larger than our final? And again, you notice that the final potential energy is less than the initial. Well, the potential energy is less than 0, but the displacement is also less than 0. And I get that the displacement and the potential energy, that quantity is positive. And we have a third negative sign, meaning that the force is towards the origin. So it all ties together. Now, again, thinking about from the previous term of the class, we have a list of conservative forces. For example, the spring force, Hooke's law, and the potential energy. And notice that if we take a derivative of the energy and insert the negative sign, we indeed end up with Hooke's law. Well, but wait, there's more. You say, wait a minute, how about the gravitational force? And I say, indeed, if we compare the potential energy for the gravitational force, if we take a derivative with respect to r, the relative position vector, we end up with Newton's law of gravity. Well, there's another force that looks awfully like gravity, namely the Coulomb force. Does there exist some scalar potential energy associated with the Coulomb force? And you as a student observer say, well, of course, that must just simply be replacing the m's with charges, replacing the gravitational constant with the Coulomb constant. And so I end up with a potential energy associated with the charge of objects. Pretty cool, huh? All right. And yes, that is why these expressions look so much like each other, right? They only differ by a derivative. Well, let's go a little further with gravity. And what I find helpful sometimes going into this is talking about topographical maps. Now, recall how to read a topographical map, or maybe what kind of information is presented on a map. So, for example, you say, hey, the lines that are drawn represent lines of constant elevation, right? Or if you prefer, you could think of, because the elevation, the height above sea level is constant, you could think of these lines of constant gravitational potential energy, right? Constant elevation, that means that your gravitational potential energy is constant. I could walk around that topographical line, say starting at 4,500, and walk around on that line. And as long as I stay on the line, my potential energy stays constant. There is no change. Next question, and you may or may not remember this. Pause the video, try to dig it out of your memory banks. Okay? But not only does a topographical map show us lines of constant elevation, but it also conveys to us the slope. So recall, how does a topographical map convey slope? Yeah, good. Remember that the closer together the lines are, the steeper the slope. Really what it's saying is that for a given distance on the map, if you cross more lines, then the slope is steeper. Whereas if you cross less lines, the slope isn't as steep. So the spacing between lines of constant elevation tell you the slope at any given point. Last thing I should point out, if I drop a ball on the hill, say right here, you know that the ball should roll from high elevation to low elevation. In other words, it should roll that way. Or if I put it right here, yeah, good, you say downhill, or here, downhill. Maybe I put the ball here. Say, okay, downhill is like this. You can see that if we drop our test ball on the topographical map, we can start mapping out a vector field. Furthermore, how do the lines of constant elevation and the orientation of the vectors representing the force, how do those two compare? Good. Hopefully you see that the forces, the vectors representing the force, are perpendicular to the lines of constant elevation, right? That should make some sense, right? They shouldn't be parallel to the lines of constant elevation, because if I walk along a line of constant elevation, there's no change in the slope, there's no change, and therefore the force in that direction should not, well, I should say the force in that direction should be zero. Okay? The place where the force is the largest is in the direction that is perpendicular to the lines of constant elevation. Convince yourself that's true. Okay, put that on a side burner for a second. Okay, here we go. So I have showed you this chart at some point, organization, and I said, hey, over here we're thinking about the interactions between system and surroundings. So I'll just put interactions. And over here on the right-hand side, we're just thinking about the underlying background that's due to the surroundings. So maybe I'll put surroundings, or sources is usually the term I use. Okay. But we can add another corner to this chart now. Namely, that if the force is conservative, which it is, the Coulomb force is, we have an analogous potential energy associated with the location of charges. If I put all of my charges into the system, so we talk about system and surroundings. If I put all of my charges just into the system, now I can think about the potential energy stored between multiple charges. And as you would expect, that potential energy is given by the quantity kQq over r. And notice if I want to go from the Coulomb force to the potential energy, I simply take a dot product with a displacement. Conversely, if I'm given the potential energy and want to find the force, I simply need to find a derivative, right? Take a derivative of the potential energy with respect to r to get the force. Now, we've already talked about how the force and the electric field are intimately related. And because the Coulomb force is conservative, there is also an intimate relationship between the Coulomb force and the potential energy between charges. This would seem to suggest that there is a fourth physical quantity that is related to either the potential energy and or the electric field. And indeed there is. You even know how to derive the expression for this physical quantity. For example, if I'm given the electric field, I simply need to do a dot product with a displacement in order to find this unknown physical quantity. And maybe I should say a negative dot product. Or if I take this unknown physical quantity and take a derivative with respect to r, I should end up with the electric field again. Similarly, you could see the back and forth relationship. If I take the potential energy and I remove the system charge, I should end up with this unknown quantity. Or I could take this unknown quantity, multiply it by my system charge to figure out the potential energy. Now you can see, just based on that, you could even tell me the units. If I take a joule and divide by a coulomb, I get this unknown physical quantity, which indeed measures how much energy per unit charge. That physical quantity that's behind the screen, we call that the electric potential. Yes, don't blame the messenger. I apologize. There's not much I can do about it. Let's see if we can get some ideas about this. First of all, notice that the electric potential is a scalar. It conveys the same information as the electric field, but in a scalar form. Much how the potential energy conveys the same information as a force, a conservative force, but it is a scalar rather than a vector. Now, some notes about the electric potential. Okay, like I said, don't blame the messenger, but I should say there is a difference between the electric potential and the electric potential energy. Oftentimes, you'll hear physicists just say the electric potential, and or maybe even just potential. What they are referring to is V, the electric potential, not the potential energy. Okay. That's an unfortunate vernacular problem. I will try as often as possible to say electric potential and electric potential energy, but I too fall into that little trap. They're closely related, but they are different physical quantities. Now, unfortunately, we have a situation where we have to make sure that we don't confuse V versus VAB versus delta V. Of course, not to be confused with V or V. Okay. And be careful, because the first one, V, we use that to represent the electric potential. Unfortunately, the electric potential is sometimes measured in units of volts. A volt, which is equal to a joule per coulomb. So not only do we have the physical quantity of the electric potential, but V is also used as a unit. Of course, if we want to find a difference in electric potential, some books will say VAB, the difference of the potential at location field point A and field point B. Other books will write it as delta V. Of course, you don't want to confuse this with the speed of an object or the velocity of an object. So you have at least 5 different ways that V is used. 7. I didn't put volume in here. So V could also be volume. So you just have to be careful. And also, unfortunately, the reality is that the context, you have to be aware of the context. Okay? And as I noted before, this conveys the exact same information as the electric field. How about this? I will give you a map of the electric potential. How many charges are present? Yeah, good. You should say 2. Remember that charges generate the electric field, right? And we can use the same sort of connection between the electric potential and the electric field that exists between the gravitational potential energy and the gravitational force. So, for example, here, instead of mapping lines of constant elevation, you can think of these lines as constant electric potentials. Okay. Or the terminology generally used is that these are called equipotentials. And the closer together the equipotentials, the stronger the field. The further apart they are, the weaker the field. So you could say, for example, immediately that there are 2 charges on this demonstration. And we could go a bit further. Although I forgot to mention it, you could say that that shaded area, you could say that those are regions where it's less than 0. There we go. Whereas over here in this lightly shaded region, these are equipotentials that are greater than 0. So if I'm using the ideas about topographical maps, you could say this must be a positive charge because the equipotentials are greater than 0 and the slope is like this, right? You can use how many lines to indicate the strength of the electric field. These are areas less than 0, and so they must be rolling downhill. If I dropped a test charge on this surface, the test charges would roll downhill, and so this must be a negative charge. In fact, a three-dimensional plot, you can kind of see it like this. Well, going back, you have a vector field, or you could also draw it as an electric potential. They convey the exact same information. Now, notice a couple things. Just like a topographical map where lines of constant elevation never intersect, the same happens for maps of the electric potential. Pause the video, convince yourself that has to be the case. It would be a strange world indeed, where if you had constant elevations that were different at the same location, right? Right? Okay. Well, good. Let's get some more practice. Given this map of the electric potential, and I've gone ahead and showed you what the value of the charges are, at which location is the electric potential the highest? Yeah, good. Right? Now I'm talking about the electric potential. An alternative phrasing would be which of these electric potential lines labeled is at the highest height, highest elevation. Okay. And the higher elevations are closer to the positive charge. Of course, lower elevations are closer to the lowest charges. And if you're going from, say, a mountaintop to a valley, there also must be some place where you're at sea level, right? 0. So in fact, we could actually say VB is greater than VA. And because A, E, and D all fall on the same line, we could say that these are all at the same potential, which of course is larger than VC, which is kind of like below sea level. Next question. How about this one? At which location will a proton, or maybe I could put a test charge, experience the largest force? Yeah, good. And here you want to remember that we can use the electric potential and how tightly packed the lines are to indicate a slope. So the alternative expression is which location are the lines packed closest together? You say, well, of course, that's E, right? Right here. Right there is the location where the slope is the steepest, and therefore, if I drop a charge at that location, it will experience the largest force. I could go the other way and say, at what location is the smallest force? Yeah, you go, okay, well, the biggest gap in spacing is like A or D. I guess I made it symmetric, so either or is perfectly fine. Also, I will point out, since we're talking about the electric potential, the electric field obeys the principle of superposition. Okay? And so the electric potential will also obey the principle of superposition. The idea being, if I have a particular location in space, a field point, say right here, I can think about the electric potential at that location due to one charge. I can think about the electric potential at that location due to the second charge. And if I add the two together, then I get the total electric potential at that location. So the total is equal to the sum of the individual contributions. Okay. Now we can play around with that a little bit more. Of course, again, you already see what's going to happen. If we have a distributed charge, then we can figure out the potential, the electric potential, by simply chopping it up into small pieces and adding everything together. Okay. Well, I think I'll leave it there for the time being. Of course, generally what we'll end up doing is dealing with charges in the electric potential. And in fact, we're going to start, when we move into circuits, the electric potential is the physical quantity that we tend to use when we think about circuits and circuit analysis. So that being the case, I'll call it quits here. Thank you for your attention. Keep up the good work. I'll see you next time.